Welcome back to The Explainer. So today we are digging into this completely fascinating and honestly kind of hilarious mystery right at the bleeding edge of AI research. We're looking at some recent work out of Stanford University that exposes a massive, glaring blind spot in state-of-the-art generative AI. We're going to explore why brilliant individual AI models, the ones that write flawless code, analyze massive data sets, and sound incredibly smart, literally fall apart when you just ask them to collaborate with each other. I mean, let's just think about this paradox for a second. How is it actually possible that these state-of-the-art AIs can pass the bar exam, diagnose complex diseases, or write a coherent essay in literally seconds, but they completely fail to split a virtual pile of wood and stone with another AI? It sounds like a joke, right? But as researchers have discovered, this total inability to do basic teamwork points to a fundamental limitation in how these models actually communicate.
So to solve this, we really need to understand the difference between two concepts, static grounding and dynamic grounding. Right now, AIs are incredibly good at the static kind. They can map language to a fixed external context, like, say, identifying objects in a photo or pulling facts from a database. But teamwork? That requires dynamic grounding. Think of two human project managers fighting over shared resources, like engineering hours and compute capacity. Neither of them sees the whole picture, so they have to state their needs, hash out trade-offs, and literally build a shared reality interactively over time. And the thing is, current AI benchmarks almost never test for this.
All right, let's look at section 1, the sandbox. To figure out what's going wrong, researchers built a sort of multi-turn negotiation game. Imagine two AI agents sharing a common pool of resources, let's say it's shapes or wood and stone, but here's the catch, and it's a big one. Each AI has a private, hidden set of projects that it wants to build. Each of those projects needs a different mix of resources, and they pay out a different number of reward points. Because their projects are completely hidden from one another, they are absolutely forced to communicate just to figure out who gets what from that shared pool. The rules they have to follow are incredibly straightforward. Step 1 is cheap talk, where the AIs get up to 5 natural language chat messages back and forth to try and negotiate. Step 2, they make a simultaneous purchase decision, basically secretly locking in the resources they want. And step 3 is the reveal. If their combined purchases exceed the shared pool, meaning they overdraw, they get penalized. And boom, both get 0 points for the round, 0. They have to play this high-stakes game iteratively over 4 rounds. Moving to section 2, the alibi. Does talking actually help? Well, the answer is a resounding yes. The researchers ran a no-talk baseline first, and under highly competitive conditions, the AI's joint efficiency was an absolutely dismal 18%. But the moment you allow them those 5 little turns of chat, their efficiency jumps massively to over 63%. So they absolutely, for sure, know how to use language to improve their outcomes. What's so interesting here is that across every single level of compatibility, whether their hidden goals heavily conflict or mostly align, allowing this cheap talk drastically reduces overdraws and boosts optimal outcomes. It proves that communication isn't just a nice-to-have, it's an absolute necessity for them to get anywhere. Okay, section 3, the 4 suspects, how coordination fails. So if they can talk, and talking helps, why do they still mess up so often? The researchers found that when AI coordination breaks down, the failures fall into 4 really distinct behavioral traps. You've got a lack of prior context, stubborn anchoring, a reliance on perfunctory fairness, and referential binding failures. Let's interrogate these one by one. Suspect number 1 is shifting partners, or basically a total lack of shared history. Think about human teamwork. We build these ad hoc conventions over time with our colleagues, right? Well, researchers found that when AIs constantly shift partners every round, their coordination totally degrades. Models actually benefit a lot from having a stable partner across rounds because it lets them establish common ground. Without that shared history, they just constantly struggle to align. Now, on the flip side, suspect number 2 is what we're calling stubborn anchoring. While having an accumulated history can help, it can also become a massive trap. Once an AI pair finds a split that just isn't terrible, meaning, they didn't overdraw and get 0 points, they get incredibly lazy. They'll just repeat that exact same suboptimal split up to 46.5% of the time. They treat their initial proposal like it's carved in stone, rather than trying to renegotiate and find a much better optimal split for both of them.
Our third suspect is the perfunctory fairness compromiser. Remember, this game is designed so that the AIs have asymmetrical, completely different needs based on their hidden projects. So the mathematically best outcome is almost never a perfect 50-50 split. And yet, in 12.5% of rounds, the agents default to asking for identical, perfectly equal quantities of resources. Why do they do this? Because it's an easy social shortcut. It entirely avoids the conversational effort of digging deep and understanding what the other agent actually needs. It's basically surface-level fairness over genuine teamwork. The final, and honestly the most hilarious suspect, is referential binding failure. Get this. In over half the rounds that resulted in a catastrophic overdraw where everyone gets 0, the AIs had actually reached a verbal agreement in the chat beforehand. One AI would say something like, "Perfect, I'll take 6 stone," acting like a total team player. But then, when it came time to submit their actual hidden purchasing action, they submitted something completely selfish and different, blowing up the entire deal. They literally fail to bind the commitments they make in speech to their actual real-world actions. Wild, right? Which brings us to Section 4, the interrogation, the full transparency test. So what happens if we just show them each other's cards and eliminate all that hidden information from the start? Well, revealing everything definitely helps lower the overdraw penalty, dropping it from 11.2% down to 3.8% in competitive scenarios. It also completely eliminates that lazy 50-50 split behavior. But here is the crazy part. Achieving the mathematically best outcome actually gets worse, dropping from 65% down to 52.5%. And that stubborn anchoring we just talked about, it essentially doubles. Even with perfect information laid out right in front of them, they lock onto a suboptimal plan super early and just flat out refuse to renegotiate. And that leads us to Section 5, the verdict, the grounding bottleneck. By ruling out basic reasoning, limits, and hidden information, we can finally isolate the true culprit here. The bottleneck lies in the interactive processes of joint plan formation. Current AIs simply lack the interactive, very human art of making a firm commitment to a joint plan and then actually executing that shared reality over time. They can exchange facts back and forth beautifully, but they cannot truly coordinate action across multiple turns of a conversation. All of this leaves us with a pretty massive implication for the future. We are rapidly moving toward a world of multi-agent systems, right? A world where we deploy autonomous AI teams to manage our schedules, book our flights, and negotiate our resources. But if these brilliant state-of-the-art models currently fail to dynamically ground reality and split a virtual pile of wood without blowing up the deal, we really have to ask ourselves, how can we fully trust them to negotiate on our behalf? It's a massive grounding gap that researchers absolutely must close before AIs can truly become our teammates. Thanks so much for joining me on this explainer. And as always, keep questioning the data.